In every film you've ever seen set in space, an explosion arrives with a roar. A ship passing overhead produces a deep, rumbling whoosh. A laser blast cracks with a sharp snap. None of it is real. If you were floating in space tonight, close enough to watch a star go supernova, you would see it happen in complete, undisturbed silence. No rumble, no shockwave. Not because the explosion wasn't loud enough, but because there was nothing out there to carry the sound to you at all. Tonight we'll figure out exactly why that's true and where the rules change. Because they do. There is sound in space, just not where you'd expect it. You'll learn why an astronaut can't hear an explosion 3 feet away, why NASA has recorded the sound of a black hole, and why the silence of space is stranger than any movie ever imagined. If you find yourself drawn into stories like this one, take a moment to like this video or subscribe. It helps more than you'd think, and it lets us keep making these late night trips together. Now, let's begin. It's worth understanding exactly why Hollywood has spent nearly a century deliberately getting this wrong, because the reasons turn out to be more interesting and more defensible from a filmmaking perspective than simple carelessness or ignorance of the underlying physics. Sound designers and directors have generally understood, going back decades, that space is genuinely silent. This isn't some accidental oversight that better research could have corrected. Ben Burtt, the legendary sound designer behind the original Star Wars films, has spoken publicly about deliberately choosing to add sound to space battles and starship flybys, specifically because silence, however scientifically accurate, tends to feel emotionally flat and disorienting to a general theatre audience conditioned by an entire lifetime of Earth-bound sensory experience, where every visible, dramatic event has always been accompanied by a corresponding sound. A massive spaceship silently gliding past the camera, however true to real physics, can read to an audience as strangely inert, even lifeless, robbing the moment of the visceral, physical sense of scale and power that a deep, rumbling engine sound naturally provides. There have been a small number of notable exceptions where filmmakers deliberately embraced accurate, silent space specifically for dramatic and thematic effect, precisely because breaking from the usual Hollywood convention can itself become a powerful storytelling tool. The 2013 film Gravity, directed by Alfonso Cuarón, famously used sudden shifts into genuine silence during certain space-based sequences specifically to disorient and unsettle audiences, and the film's own marketing leaned directly into this scientific accuracy with the tagline "In space, no one can hear you scream," itself a direct echo of the tagline originally used decades earlier for the 1979 film Alien, which employed the same scientifically accurate silence as a central element of its own horror atmosphere, using the complete absence of sound during certain space set sequences to heighten tension, precisely because it violated audience expectations built up by decades of louder, more conventional science fiction sound design. In both cases, the directors understood that genuine silence, used sparingly and deliberately, could produce a more powerful emotional effect specifically because it broke so sharply from the noisy space combat and starship engine roars audiences had been conditioned to expect from nearly every other entry in the genre. This tension between scientific accuracy and emotional impact is worth keeping in mind throughout the rest of tonight's video, because it's a genuinely useful lens for understanding why the popular imagination of space remains so persistently, confidently wrong about something as fundamental as whether sound exists there at all. It's not that the information isn't available, it's that the true, accurate answer, complete and total silence, is dramatically difficult to work with, disorienting rather than thrilling in the hands of most filmmakers, and so an entire century of popular culture has quietly, collectively agreed to get this one detail wrong, again and again. Specifically because the true answer doesn't make for very good cinema. Let's start with the basics, what sound actually is at the level of physics, before we go any further. Sound is not a thing that travels through empty space the way light does. Sound is a mechanical pressure wave, a pattern of compression and rarefaction, squeezing and releasing, moving through a physical medium, air, water, steel, wood, or anything else made of matter. When you speak, your vocal cords vibrate, pushing against the air molecules immediately surrounding them. Those molecules bump into their neighbours, compressing them slightly, and those neighbours bump into their own neighbours in turn, passing the disturbance outward in a chain reaction, molecule colliding with molecule, in a wave of alternating high and low pressure that radiates outward from the source in every direction, like ripples spreading across a pond, until eventually that wave reaches your ear, vibrates your eardrum, and your brain interprets the pattern of vibration as sound. This is worth sitting with for a moment, because the entire concept of sound depends, completely and unavoidably, on the existence of something physical to do the vibrating. No air, no water, no solid material of any kind means no molecules to bump into each other, which means no chain reaction of compression and rarefaction, which means, quite simply, nothing for your ear to ever detect. Sound isn't being blocked or muffled in a vacuum. It's not weakened, dimmed, or reduced to some faint whisper you'd need better hearing to catch. It simply cannot exist there at all, in the same way a wave cannot exist on a pond that has no water in it. The wave isn't hiding. There's nothing for the wave to be made of. This fact, that sound requires a medium and simply cannot exist without one, wasn't always obvious, even to trained scientists, and it's worth understanding how humanity actually figured this out, because the experiment involved is elegant enough to explain in a single sentence, and reveals a great deal about how careful, curious observation eventually settles even deeply counterintuitive questions about the physical world. In the mid-1600s, the English scientist Robert Boyle, one of the founding figures of modern experimental chemistry and physics, conducted a landmark experiment using a device called a vacuum pump, recently invented by the German scientist Otto von Guericke, to systematically remove air from a sealed glass container holding a ticking watch or a ringing bell. As Boyle pumped more and more air out of the container, observers listening from outside reported that the sound of the ticking or ringing grew steadily fainter, and eventually, once the vacuum pump had removed as much air as the technology of the era allowed, the sound disappeared entirely, even though the watch could still be seen, through the glass, continuing to visibly tick away exactly as before. Boyle's experiment, first published in 1660, provided some of the first rigorous, controlled experimental evidence that sound requires a physical medium to propagate, a genuinely significant scientific finding at the time, since prior to this kind of careful systematic testing, philosophers and natural scientists had held a range of competing, largely untested assumptions about the fundamental nature of sound, some treating it as an intrinsic property of the vibrating object itself, capable of existing and radiating outward regardless of its surroundings, rather than correctly understanding it as a disturbance requiring some external substance to actually carry it anywhere. It's a genuinely elegant piece of scientific history worth remembering, because it establishes that the no sound in a vacuum principle isn't some modern space-age discovery invented once humanity actually reached orbit. It's a more than 360-year-old, carefully demonstrated physical fact, established using nothing more sophisticated than a glass jar, a hand-cranked vacuum pump, and a ticking watch, centuries before anyone had any concept of what a rocket, a satellite, or a spacewalk might someday actually involve. This same basic demonstration, a bell or a ringing device inside a bell jar, gradually silenced as air is pumped out, remains one of the most common classroom physics demonstrations used today specifically to teach students this exact principle. Still relying on essentially the same core method Boyle first employed nearly 4 centuries ago, updated only with modern vacuum pump technology, capable of achieving a considerably more complete vacuum than anything available in the 17th century. It's a nice reminder that some of the most important, most fundamental truths about how the physical universe works were established using remarkably simple tools, long before anyone had any practical need to actually apply that knowledge to a real spacecraft or a real astronaut. Space, for the overwhelming majority of its volume, is about as close to a true, perfect vacuum as anything we've ever measured. The interplanetary space between Earth and Mars contains, on average, somewhere in the range of 5 to 10 particles per cubic centimetre, mostly stray protons and electrons streaming outward from the Sun as part of the solar wind. By comparison, the air you're breathing right now, in whatever room you're sitting in, contains roughly 25 quintillion molecules in that same cubic centimetre of space. 25 quintillion is a 25 followed by 18 zeros. The gap between essentially nothing and the air around you isn't a modest difference of scale. It's a difference so enormous that ordinary numbers stop being useful for describing it, and it's precisely this emptiness, this near total absence of anything solid enough to bump into anything else, that makes space fundamentally, physically incapable of carrying a sound wave from one point to another. It's worth understanding, in a little more detail, exactly how the human ear converts these pressure waves into the experience of hearing, because the mechanism itself is a genuinely elegant piece of biological engineering, and understanding it makes the vacuum silence of space feel even stranger by direct comparison, when a sound wave, a travelling pattern of compressed and rarefied air molecules, reaches your head, it enters the ear canal and strikes the eardrum, a thin, taut membrane that vibrates in direct response to the changing air pressure hitting it, compressing inward as a high-pressure region arrives, and springing back outward as the following low-pressure region passes. These vibrations are then transmitted through 3 tiny bones in the middle ear, the malleus, incus, and stapes, sometimes known by their more familiar names, the hammer, anvil, and stirrup, the smallest bones in the entire human body, which mechanically amplify the vibration and pass it along to the cochlea, a fluid-filled, spiral-shaped structure in the inner ear, lined with thousands of microscopic hair cells. As the vibration reaches the cochlea, it creates travelling waves through the fluid inside, and these waves bend the microscopic hair cells in patterns that correspond to different frequencies, triggering electrical signals that travel along the auditory nerve directly to the brain, where they're finally interpreted as the specific sound you're hearing. Every single stage of this remarkable biological chain, from the vibrating eardrum to the mechanically amplifying middle ear bones to the fluid-filled cochlea, depends entirely on the existence of an initial pressure wave arriving from outside to set the whole process in motion in the first place. Your ear is, in the most literal sense, a beautifully evolved instrument specifically built to detect mechanical pressure waves travelling through air, and it has absolutely nothing to detect, no matter how sensitive or well designed, in an environment where no such pressure wave exists at all. This is worth remembering the next time you picture an astronaut floating in the vacuum of space. Their ears are not malfunctioning, damaged, or somehow blocked. They are functioning exactly as intended, a remarkably sensitive biological instrument. Evolved over hundreds of millions of years specifically to detect air pressure vibrations, simply sitting in an environment that has removed the one thing that instrument was ever built to detect. It's worth noting, too, that the specific range of frequencies any given species can detect varies considerably across the animal kingdom, itself a product of each species' own particular evolutionary pressures and ecological needs, though every single example still depends entirely on the same fundamental requirement of a physical medium to carry the vibration in the first place. The average human ear can detect frequencies ranging from roughly 20 Hz at the low end to approximately 20,000 Hz at the high end. Though this upper range diminishes considerably with age, a phenomenon called presbycusis that affects most people to some degree by later adulthood. Elephants can detect and produce infrasound, extremely low-frequency vibrations below the threshold of human hearing, sometimes as low as 5 Hz, which they use to communicate over remarkably long distances. In part because low-frequency sound waves lose energy more slowly over distance than high-frequency ones, allowing elephant infrasound calls to travel several kilometres, in some studies documented travelling considerably further under favourable atmospheric conditions. Bats and dolphins, by contrast, specialise in the opposite extreme, detecting and producing ultrasound, frequencies well above the range of human hearing, in some bat species reaching well over 100,000 Hz, 5 times higher than the upper limit of human perception, an adaptation specifically suited to their use of echolocation. Echolocation itself is worth explaining briefly here, because it represents one of the most sophisticated uses of sound found anywhere in the animal kingdom, and because it depends, once again, entirely on the presence of a physical medium capable of carrying both the outgoing sound and its returning echo. Bats and toothed whales, including dolphins, produce rapid sequences of high-frequency sound pulses and listen carefully for the echoes that bounce back after striking nearby objects, using the precise timing, intensity, and frequency shift of each returning echo to construct a remarkably detailed 3-dimensional picture of their surroundings, detailed enough to allow a bat to detect and capture a single small flying insect in complete darkness, or to allow a dolphin to distinguish between subtly different types of fish hidden beneath murky water. This entire extraordinarily sophisticated biological sonar system depends, at every single stage, on air or water actually being present to carry both the original outgoing pulse and its returning echo, a bat or dolphin transported instantly into the vacuum of space would find echolocation, along with every other form of hearing, completely and immediately non-functional. Its elaborate biological sonar rendered entirely useless the moment there was no longer any medium left for its carefully engineered sound pulses to travel through. This is worth contrasting directly with how light behaves, because the two often get confused in casual conversation, treated as though they follow the same basic rules, just at different speeds. Light is not a mechanical wave requiring a physical medium at all. It's an electromagnetic wave, a self-propagating oscillation of electric and magnetic fields that requires nothing to vibrate against, no molecules, no medium, nothing but the fundamental structure of space-time itself. This is exactly why light from the sun, and from every star we've ever observed, can cross the essentially empty vacuum of interstellar space and still reach us, while sound, produced by that exact same star, a sun that is, at every moment, undergoing constant, violent thermonuclear fusion, extraordinarily loud by any measure that matters here on Earth, cannot travel even a single inch beyond the sun's own outer atmosphere before running out of anything to push against. Let's actually sit with that fact for a moment, because it's stranger than it first sounds. The sun is, by any reasonable definition, one of the loudest objects that exists anywhere near us. Its surface is in a state of constant, roiling convection, boiling plasma, erupting upward, and sinking back down in massive churning cells roughly the size of Texas, each one rising and falling in a cycle that takes around 10 minutes to complete. Solar flares release energy equivalent to billions of hydrogen bombs detonating simultaneously. Every single one of these processes generates genuine, real, physical sound waves, pressure disturbances rippling through the sun's own dense plasma, exactly the way sound ripples through Earth's atmosphere. Paleoseismologists, scientists who study the sun's internal structure, actually use these sound waves directly, tracking how they travel through and reflect off different layers inside the sun to build detailed maps of its internal structure, in a technique remarkably similar to how geologists use seismic waves to study the interior of the Earth after an earthquake. But none of that sound ever leaves the sun. The moment those pressure waves reach the sun's outer atmosphere, the corona, where the plasma thins out dramatically and eventually gives way to the near vacuum of interplanetary space, they simply run out of material to keep propagating through. The sound doesn't travel outward and gradually fade. The way a shout becomes quieter the further you get from the person who made it. It stops, abruptly and completely, at the boundary where there's no longer anything for it to keep pushing against, roughly where the sun's outer atmosphere thins into the solar wind. If you could somehow survive, unprotected, floating just outside that boundary, close enough to see solar flares erupting and titanic waves of plasma crashing across the sun's surface in real time, you would witness all of it in perfect, complete silence, watching some of the most violent events in the entire solar system unfold without a single sound reaching you. Not because you were too far away, but because sound itself simply has nowhere left to go. This raises an obvious and important question. If sound can't travel through the vacuum of space at all, how does anything happening on a spacecraft or on the surface of another planet ever get heard by anyone? And the answer reveals something important about how audio actually works aboard the International Space Station, and why astronauts, despite floating in the same essentially soundless vacuum as everything else out there, are not living in total silence themselves. The International Space Station is not exposed to the vacuum of space. It's a sealed, pressurized structure, filled with a breathable atmosphere, maintained at a pressure similar to what you'd experience at sea level here on Earth. And inside that pressurized volume, sound behaves in exactly the same way it behaves inside your own house, propagating through the air as ordinary pressure waves, bouncing off walls, travelling to your ears in the completely normal, familiar way. In fact, one of the persistent, genuine challenges of living aboard the IS involves managing noise levels, not the absence of sound, but the surprising abundance of it. The station is filled with pumps, fans, air circulation systems, and life support equipment running constantly, all of it generating continuous background noise that astronauts have described as comparable to the hum of a busy office or a running dishwasher, present at all times, everywhere throughout the station, simply because there is no way to ventilate the sound outside without also venting the breathable air that makes the entire station survivable in the first place. This background noise turns out to be a genuinely serious concern for long-duration spaceflight, not merely an inconvenience. NASA has conducted extensive acoustic monitoring aboard the IS, and multiple studies have documented measurable, sustained hearing loss among astronauts who have completed long-duration missions, a consequence of continuous exposure to background noise levels that, while not dangerously loud in the way a jet engine or a construction site might be, are sustained for months at a time with no genuine escape, since astronauts can't simply step outside for a quiet walk the way someone living in a noisy apartment building on Earth eventually can. NASA guidelines specify maximum acceptable noise levels for different modules of the station, and considerable engineering effort has gone into designing quieter fans, quieter pumps, and better sound insulation specifically to address this. An entire branch of spacecraft engineering dedicated to managing a problem that only exists because human beings inside a pressurized, air-filled structure remain just as capable of hearing and just as vulnerable to the effects of chronic noise as they would be in any ordinary building back on Earth. This acoustic engineering challenge has a history stretching back well before the IS itself. NASA's earlier Skylab space station, which operated in orbit through the 1970s, and the Russian Mir space station, continuously crewed through much of the 1980s and 1990s, both faced documented noise complaints from their crews. And lessons learned from monitoring astronaut hearing across these earlier programs directly informed the acoustic design standards eventually applied to the International Space Station once its construction began in 1998. Some of the noisiest individual pieces of equipment ever operated aboard the station have included older generation air circulation fans, and the treadmill and resistive exercise equipment astronauts use daily to help counteract the bone and muscle loss caused by extended time in microgravity. Equipment that, ironically, is itself essential specifically because it helps keep astronauts physically healthy enough to survive the very same long-duration missions during which chronic noise exposure poses its own separate health risk. Engineers have responded over the years with a range of solutions, including redesigned, quieter fan blades, additional acoustic foam paneling in especially noisy modules, and in some cases requiring astronauts to wear hearing protection during particularly loud operational periods, an ongoing, iterative engineering effort that continues today. refined mission after mission, as NASA and its international partners continue gathering more data on exactly how chronic, low-level noise exposure affects astronauts across increasingly long-duration missions, including the kind of multi-year missions currently being planned for eventual crewed travel to Mars. Now consider what happens the moment an astronaut leaves that pressurized environment and steps outside for a spacewalk, formerly called an extravehicular activity, or EVA. Inside a spacesuit, an astronaut is once again surrounded by a small, sealed volume of pressurized breathable air, meaning sound can still propagate normally within the suit itself. Astronauts can hear their own breathing, the hum of the suit's own internal life support systems, and communications relayed through their headset. But the moment any sound-producing event happens outside that suit, a small impact against the suit's exterior, a tool being used nearby, anything at all occurring in the vacuum surrounding them, none of it reaches the astronaut's ears as sound in any conventional sense, because there's no air outside the suit to carry that vibration to them. There is, however, a genuinely strange and lesser-known exception to this, one worth explaining carefully, because it reveals something important about how sound can still travel under very specific, unusual circumstances, even in an airless environment. If a solid object strikes the exterior of a spacesuit or the exterior of a spacecraft directly, the vibration from that impact can travel through the solid material itself, through structure-borne conduction, rather than through the air. And if that vibrating material happens to be in direct physical contact with something else, an astronaut's glove pressed against a spacecraft's hull, for instance, that vibration can, in principle, be felt or even faintly heard through the astronaut's own suit and body, conducted mechanically through solid matter rather than through empty space. This is precisely the same physical principle by which you can press your ear against a wall to hear a conversation happening in the next room, or press your ear against a train track to feel a train approaching long before you could ever hear it through open air. Sound, it turns out, doesn't strictly require air specifically. It requires some form of matter, dense enough and connected enough to carry a mechanical vibration. And solid materials in direct contact with each other can do this job just as well as air can, sometimes even more efficiently, since solids are generally denser and more rigid than air, allowing vibrations to travel through them faster and with less energy lost along the way. This single fact, that sound requires matter but not specifically air, is the key that unlocks nearly every genuine exception to the space is silent rule, and it's worth carrying forward into everything else we're going to discuss tonight. Sound in space isn't impossible. It's simply, overwhelmingly, extremely locally constrained, capable of existing only in the specific. Comparatively rare places where enough matter happens to be present, and gone the instant you move beyond wherever that matter runs out. It's worth taking a moment to explore exactly how dramatically the speed and character of sound changes depending on what medium it happens to be travelling through, because this variability is part of why sound in space, wherever it does technically exist, tends to behave in such strange, unfamiliar ways compared to the sound we're used to on Earth. In dry air at room temperature, sound travels at approximately 343 meters per second, or about 767 miles per hour. In water, a considerably denser medium, where molecules are packed much more tightly together and can transmit a pressure disturbance from one to the next much more quickly. Sound travels at roughly 1,480 meters per second, more than 4 times faster than in air. In steel, denser and more rigid still, sound travels at approximately 5,960 meters per second, nearly 17 times faster than in ordinary air. The general physical principle underlying all of this is that sound tends to travel faster through denser, more rigid materials, where individual molecules or atoms sit closer together and are more strongly bonded to their neighbours, allowing a pressure disturbance to be passed along more quickly, and slower through lighter, more diffuse, more loosely connected materials, where each molecule has to travel further before bumping into the next one to continue passing the wave along. This principle explains exactly why sound on Mars, with its thin, 30 times less dense than Earth atmosphere, travels more slowly and attenuates more quickly than sound on Earth, and why sound on Venus, with its 92 times denser atmosphere, would likely travel unusually efficiently by comparison. It also explains something worth returning to about the Sun itself, because the Sun's interior consists of extremely dense, compressed plasma. Especially near its core, sound waves generated by the Sun's own internal convection and nuclear fusion processes actually travel through the Sun's interior at speeds far exceeding anything possible in air or even in steel. In some regions of the solar interior reaching speeds on the order of hundreds of kilometers per second, a direct consequence of just how extraordinarily dense and compressed matter becomes deep within a star. Helioseismologists exploit this exact property, tracking how these internal sound waves travel at different speeds through different layers of the Sun's interior. Since regions of differing density, temperature, and composition all affect the local speed of sound in subtly different, measurable ways, allowing scientists to build remarkably detailed maps of the Sun's internal structure, its rotation rate at different depths, and even indirect evidence of activity happening on the far side of the Sun, entirely hidden from any direct telescope observation. Using nothing more than the way sound waves ripple through and reflect off different internal layers, the same basic principle geologists use to study the deep interior of the Earth using seismic waves generated by earthquakes. Let's talk too about the Sun's actual surface convection itself, because the scale involved is worth appreciating more fully than a passing mention allows. The turbulent, granulated pattern visible on the Sun's surface through a solar telescope, sometimes called solar granulation, consists of individual convection cells, each one roughly the size of Texas, rising and falling in a churning cycle that takes approximately 10 minutes to complete. Hot plasma rising to the surface from deeper within the Sun, cooling slightly, and sinking back down to be reheated over and over across the Sun's entire visible surface simultaneously. Each of these individual convection cells generates genuine acoustic energy as it rises, cools, and sinks, and the combined acoustic output of billions of these simultaneous convection cells produces the pressure waves helioseismologists study, and genuinely staggering amount of real, physical sound energy constantly generated across the entire surface of a star, roughly 1.4 million kilometers in diameter, all of it entirely trapped within the Sun's own dense plasma, none of it ever escaping into the vacuum beyond, exactly the same way a shout inside a sealed, soundproofed room never reaches anyone standing outside, no matter how loud the shout actually is within that sealed space. Let's talk about one of the most famous and most misunderstood exceptions to this rule: NASA's black hole sound recordings, which generated enormous public attention when they were first widely shared, and which have circulated online in various forms for years since, often with a genuinely accurate but easily misunderstood framing that NASA has recorded the sound of a black hole. Understanding exactly what this actually means and what it doesn't mean requires walking through the real science carefully. It's worth understanding a little about the instrument responsible for this discovery in the first place. Because Chandra represents a genuinely different kind of telescope from the more familiar visible light observatories most people picture when they think of astronomical imaging. Launched by NASA in July 1999 aboard the Space Shuttle Columbia, the Chandra X-ray Observatory is specifically designed to detect X-ray radiation, an extremely high-energy form of electromagnetic radiation produced by some of the hottest, most violent phenomena in the universe, material heated to millions of degrees as it falls toward a black hole, the aftermath of supernova explosions, and the superheated gas filling galaxy clusters, exactly the kind of gas surrounding the Perseus Cluster's own central black hole. Earth's atmosphere blocks X-rays from reaching the ground almost entirely, which is precisely why Chandra, like nearly all X-ray telescopes, needed to be placed in space in the first place, orbiting far above the atmospheric layer that would otherwise prevent this particular form of radiation from ever reaching a ground-based instrument at all. Chandra's orbit is itself unusual for a space telescope, an elliptical path that carries it more than a third of the way to the moon at its farthest point, chosen specifically to keep the observatory clear of interference from the belts of charged particles trapped within Earth's own magnetic field. The same Van Allen radiation belts we've discussed at length in previous videos on this channel. At the centre of the Perseus galaxy cluster, an enormous, gravitationally bound collection of hundreds of individual galaxies, located roughly 240 million light-years from Earth, sits a supermassive black hole. This black hole is surrounded by an immense cloud of superheated gas, heated to temperatures exceeding 180 million degrees Fahrenheit, filling the space between the cluster's galaxies. In 2003, astronomers using NASA's Chandra X-ray Observatory discovered something genuinely remarkable embedded within this hot gas: pressure waves, real physical ripples of compression and rarefaction, moving outward through the gas from the region surrounding the black hole, propagating through that superheated material in essentially the same physical manner that sound waves propagate through. Earth's atmosphere, since the underlying physics of pressure waves moving through any sufficiently dense medium, follows the same basic principles regardless of what that medium happens to be made of. These pressure waves were genuinely, actually there, embedded in real astronomical data, not a metaphor or a stylistic reinterpretation applied afterward for dramatic effect. But their actual pitch, the true frequency of the pressure oscillations astronomers detected, was almost inconceivably low, corresponding to a note roughly 57 octaves below middle C, with a single wave cycle taking approximately 10 million years to complete. For comparison, the lowest note the human ear can detect under any circumstances has a frequency on the order of 1/20th of a second per cycle. The actual true pitch of these black hole pressure waves sits so far below anything a human ear could ever perceive, even in principle, that describing it as inaudible almost understates the gap involved. It would be inaudible to literally anything with ears, on any planet, using any biology that has ever evolved, because it operates on a time scale measured in millions of years rather than fractions of a second. What NASA actually released in a project called Sonification involved taking this real, measured data and mathematically scaling it upward by 57 and 58 octaves, roughly speeding up the underlying signal by a factor of 144 quadrillion, until its frequency finally landed somewhere within the narrow range of pitches a human ear can actually detect. The eerie, haunting audio that resulted, and which subsequently went viral, being requested for use in documentaries by the BBC and Netflix, is genuinely derived from real astronomical measurements, but it is not. In any meaningful sense, what a black hole sounds like, in the way that phrase tends to be understood by a casual listener. It's closer to translation than recording, a bit like taking a photograph captured in ultraviolet light, entirely invisible to human eyes, and digitally shifting its colours into the visible spectrum so people can look at it. A legitimate and scientifically useful technique, but one that involves a real, significant transformation of the original data, not simply playing back something that was always secretly audible all along. It's worth appreciating why astronomers cared about these pressure waves scientifically in the first place, beyond their eventual, unplanned popularity as a piece of viral audio, because the discovery addressed a genuinely important open question in astrophysics. Galaxy clusters like Perseus contain vast quantities of superheated gas that, according to straightforward thermodynamic calculations, should be cooling and condensing over time, theoretically collapsing inward to form enormous numbers of new stars at a rate far higher than astronomers actually observe happening in real galaxy clusters. This mismatch between prediction and observation, sometimes called the cooling flow problem, puzzled astrophysicists for years, since something clearly had to be continuously reheating this gas, preventing the runaway cooling and star formation their models predicted, but their telescopes never actually found. The discovery of these pressure waves rippling outward from the central black hole provided a compelling piece of the answer, the black hole itself, through repeated eruptions of energetic jets and outbursts as it consumes surrounding material, appears to be continuously pumping energy back into the surrounding gas. These very pressure waves acting as a genuine physical heating mechanism, keeping the cluster's gas hotter than it would otherwise be, and helping explain why runaway cooling and star formation don't occur nearly as often as the simpler thermodynamic models originally predicted. In this sense, the sound NASA eventually made audible wasn't merely a curiosity. It represented direct physical evidence of one of the most important self-regulating feedback mechanisms astronomers have identified anywhere in the universe: a black hole, sitting at the centre of a cluster containing hundreds of individual galaxies, quietly influencing the evolution of everything around it, not through gravity alone, but through literal, physical pressure waves, rippling outward across hundreds of thousands of light years, at a pitch 57 octaves too low for anything with ears to ever have noticed on its own. It's worth being precise here, because this distinction matters for understanding what's actually happening throughout this entire field of research, sometimes called data sonification more broadly. NASA has released similar sonifications of numerous other astronomical phenomena beyond the Perseus black hole, including a separate sonification of the black hole at the centre of the M87 galaxy, and various sonifications translating telescope imagery, X-ray, visible light, and radio wavelength data captured by instruments like the Chandra X-ray Observatory, the Hubble Space Telescope, and the Atacama Large Millimeter Array into audible tones, typically by mapping different wavelengths of light to different pitches, and scanning across an image to generate a sequence of notes. These sonifications serve a genuinely valuable scientific and educational purpose, in particular making certain kinds of astronomical data accessible to blind and visually impaired audiences who cannot directly view telescope imagery but can meaningfully engage with a sonified version of the same underlying data. But in every single case, what's being presented is a deliberate, carefully constructed translation of data that was never actually audible in its original form, transformed specifically to become audible, rather than a genuine, unaltered recording of sound as it actually exists and travels through space. This distinction becomes even more important once you consider the deeper physical reality underlying the Perseus black hole case specifically. Even setting aside the octave shifting required to make the frequency audible at all, there remains the more fundamental question of whether these pressure waves could ever have reached human ears in their original unaltered form, even hypothetically, even with technology capable of somehow detecting frequencies that low. And the answer again comes back to the same core physical requirement we started with tonight. Pressure waves require a physical medium to travel through, and this only works within the Perseus cluster specifically, because that region of space isn't actually a true vacuum at all. It's filled with an enormous, if extremely diffuse by everyday standards, cloud of superheated gas, hundreds of thousands of light years across, dense enough, even at temperatures exceeding 180 million degrees, to support the propagation of a genuine pressure wave, exactly the same way Earth's atmosphere supports the sound waves produced by your own voice. Move outside that gas cloud, into the truly empty vacuum beyond the cluster's boundaries, and even this exotic, millions of years per cycle pressure wave would have nothing left to propagate through, exactly like every other sound we've discussed tonight. This same underlying principle, sound requiring matter, any matter, dense enough to carry a pressure wave, explains every other genuine instance of sound-like phenomena detected elsewhere in space. NASA's Voyager spacecraft, which we've discussed at length in previous videos on this channel, carry instruments capable of detecting plasma wave activity, oscillations in the density of charged particles present in the thin plasma of interplanetary and interstellar space. When Voyager 1 crossed the heliopause in 2012, leaving the Sun's protective bubble and entering true interstellar space, its plasma wave instrument detected oscillations in the surrounding interstellar plasma, and NASA scientists subsequently converted this data into audible sound as well, producing an eerie tonal recording that circulated widely online, often described in headlines as the sound of interstellar space. Once again, this represents genuine, real data, plasma oscillations that Voyager's instruments directly measured, converted into an audible frequency range through deliberate scientific translation, rather than a literal recording of ambient sound that any observer floating nearby could have naturally heard with unaided human ears. The interstellar medium, while unimaginably more sparse than Earth's atmosphere, is not a perfect, zero-density vacuum either. It contains enough charged particles to support these plasma wave oscillations, in the same broad sense that the Perseus cluster's hot gas is sparse by Earth standards, but still dense enough to carry the pressure waves NASA's Chandra Observatory detected there. Pulsars offer another genuinely fascinating example of this same general category of sonification, though the underlying physics involved is different again from either the Perseus black hole or Voyager's plasma waves. A pulsar is the incredibly dense, rapidly rotating remnant of a massive star that has collapsed following a supernova explosion, a neutron star, typically no larger than a modest city in diameter, but containing more mass than our entire sun. Compressed into that impossibly small volume, pulsars emit powerful, focused beams of electromagnetic radiation from their magnetic poles, and because the star itself is spinning rapidly, sometimes hundreds of times per second, these beams sweep across the sky like a cosmic lighthouse, and if Earth happens to lie in the path of that sweeping beam, radio telescopes detect a series of extremely regular, rapid pulses of radio energy, arriving with a precision so consistent that some pulsars rival the accuracy of atomic clocks here on Earth. When astronomers convert the timing of these pulses directly into audio, playing each detected pulse as an audible click or tone, the resulting sound is often described as an eerie, rapid, ticking or buzzing pattern, and this technique has been used both for genuine scientific analysis, helping researchers study subtle variations in a pulsar's rotation, and for public outreach, giving audiences an intuitive, audible sense of just how remarkably fast and regular these cosmic lighthouses actually are. Once again, though, it's worth being precise about what's actually happening. A pulsar's emissions are electromagnetic radiation, radio waves, fundamentally the same category of phenomenon as visible light. And like all electromagnetic radiation, they require no medium at all to travel through space. What gets converted into sound here isn't a pressure wave at all, but rather the timing and pattern of arrival of electromagnetic pulses, translated into an audible rhythm for human comprehension, a conceptually different kind of sonification from the Perseus black hole's genuine acoustic pressure waves, but one that produces an equally compelling and equally often misunderstood sound of space recording. There's one more sonification project worth mentioning, because it deals with perhaps the oldest signal in the entire universe, the cosmic microwave background radiation, the faint uniform afterglow of the Big Bang itself, discovered accidentally in 1965 and detectable today as a nearly uniform hiss of microwave radiation arriving from every direction in the sky. Researchers have created audio sonifications of this cosmic microwave background data as well, translating subtle temperature variations detected across the sky by satellites like NASA's MAP and the European Space Agency's Planck mission into audible tones, giving listeners an intuitive way to appreciate the subtle patterns and fluctuations embedded within what is, at first glance, an almost perfectly uniform signal. As with every other sonification discussed tonight, this represents a deliberate, valuable scientific and educational translation of real data into an audible format, not a literal recording of some ancient sound that was always secretly there, since electromagnetic radiation, exactly like the radio pulses from a pulsar, has never needed a physical medium to travel through space in the first place, and was never audible in any literal sense to begin with at any point in the 13.8 billion years since the Big Bang first produced it. Before we move to Mars, it's worth addressing the Moon directly, because it represents perhaps the purest, most extreme example of total sonic silence that any human being has ever personally experienced. The Moon has no meaningful atmosphere whatsoever. Its surface pressure, measured in the range of a few trillionths of Earth's own atmospheric pressure, a condition so close to a true vacuum that scientists generally classify it as an airless body rather than a world with an extremely thin atmosphere. This means the 12 Apollo astronauts who walked on the lunar surface between 1969 and 1972 experienced something no human beings had ever experienced before, or, for that matter, have experienced since, standing on a solid, physical surface, in direct sunlight, surrounded by scenery, all while existing within an environment that was, beyond the confines of their own spacesuits, completely and totally incapable of carrying any sound at all. It's worth noting that the Apollo missions did carry genuine scientific instruments capable of detecting real vibration on the moon, though not in the form most people might expect. Beginning with Apollo 11, astronauts deployed seismometers directly onto the lunar surface, instruments specifically designed to detect moonquakes, seismic vibrations travelling through the moon's interior, in much the same way seismometers on Earth detect earthquakes, and in much the same way NASA's later InSight lander would go on to detect Marsquakes on Mars decades afterward. These lunar seismometers detected a genuinely surprising and scientifically valuable phenomenon, unlike Earth, where seismic vibrations from an earthquake typically fade out within a matter of minutes as they're absorbed and scattered by the planet's varied, layered, water-rich interior. Moonquake vibrations detected by the Apollo seismometers sometimes continued ringing and reverberating for as long as an hour after the initial event, a phenomenon scientists attribute to the moon's unusually dry, brittle, and structurally uniform interior, which allows seismic energy to persist and bounce around for far longer than it would on a geologically more complex world like Earth. Apollo astronauts, in a memorable and widely cited demonstration, even deliberately created an artificial seismic signal by intentionally crashing their spent lunar module ascent stages into the moon's surface after completing their missions, allowing mission scientists back on Earth to study, in controlled detail, exactly how this unusual, long-ringing seismic behaviour propagated through the moon's interior. None of this, it's worth being clear, represents sound in the sense we've been discussing throughout tonight's video, since these are vibrations travelling through solid lunar rock rather than pressure waves travelling through any kind of atmosphere. But it's a genuinely fascinating, closely related example of how vibrational energy, even in the total absence of any air whatsoever, can still behave in strange and scientifically revealing ways, so long as there remains some solid physical structure available to carry it. There's a genuinely fascinating detail buried inside the Apollo mission recordings that's worth explaining carefully, because it's been a persistent source of confusion for decades. Apollo astronauts can be heard, in mission recordings, describing sounds associated with events happening on the lunar surface, including, famously, a distinct thump or vibration reported by several crews in association with the lunar module's own structure after landing, sounds that seemed, on first listen, to contradict everything we've just established about sound requiring an atmosphere to propagate. The actual explanation involves exactly the same principle of structure-borne, solid conducted sound we discussed earlier in relation to spacesuits, any vibration occurring directly within the solid structure of the lunar module itself. Thermal contraction of the module's metal skin as it cooled after the intense heat of descent, for instance, could transmit directly through the module's rigid frame and be picked up by equipment or felt by an astronaut in direct physical contact with the structure, without ever needing to pass through the vacuum outside at all. This is precisely the same reason astronauts could hear their own suit's internal machinery, or feel vibrations transmitted through their boots while walking on the lunar surface, despite the complete absence of any atmosphere capable of carrying sound through open space between them and anything else. Apollo 11's Buzz Aldrin, reflecting years later on the experience of standing on the moon, described the silence there as profound, in a way that's difficult to convey to anyone who hasn't experienced true vacuum-level silence directly. A stillness broken only by the sound of his own breathing and the radio chatter relayed through his helmet, while the vast, sunlit landscape stretching out in every direction around him remained, regardless of anything happening within it, permanently and totally silent. Even the astronaut's own footsteps across the lunar surface, footsteps that would produce a familiar crunching sound on Earth as boots compress soil and kick up loose material, produced no sound whatsoever outside the astronauts' suits, since there was no air present on the moon's surface to carry that vibration to anyone's ears. Any astronaut walking near enough to see a colleague's boot pressing into the lunar regolith would have seen the dust kick up and settle in a hauntingly silent, slow-motion arc. Unlike the sound-accompanied dust clouds instantly familiar from any comparable action on Earth, since the moon's weaker gravity, roughly 1/6 of Earth's, combined with the total absence of air resistance, caused kicked-up lunar dust to travel in long, low, silent parabolic arcs rather than the quick, sound-accompanied puffs a similar action would produce here. Let's turn now to the planets within our own solar system, because this is where the question of sound in space becomes genuinely relevant to a place a human being might actually, someday, physically stand. Mars, unlike the near-total vacuum of interplanetary space, does have an atmosphere, thin but real, composed primarily of carbon dioxide, with an average surface pressure less than 1% of Earth's own atmospheric pressure at sea level. This means sound genuinely can, and does, travel across the Martian surface, though not in quite the same way it does here on Earth. NASA's Perseverance rover, which landed on Mars in February 2021, carries onboard microphones specifically designed to capture audio directly from the Martian surface, becoming the first mission in the history of Mars exploration to record and transmit sound recorded from another planet's surface back to Earth. The recordings that resulted were genuinely fascinating to planetary scientists, revealing something they hadn't fully anticipated beforehand. Sound behaves noticeably differently in Mars's thin, cold, carbon dioxide-dominated atmosphere than it does in Earth's thicker, warmer nitrogen-oxygen atmosphere. Because Mars's atmosphere is so much less dense than Earth's, sound travels through it more slowly, and higher-pitched sounds in particular attenuate or fade out, considerably faster than they do on Earth, meaning a sound that might carry clearly over a substantial distance here would become noticeably muffled and quieter much more quickly on the Martian surface. Researchers analysing Perseverance's audio data found that the speed of sound on Mars actually varies depending on pitch, with higher frequency sounds travelling at a slightly different speed than lower frequency sounds, a genuinely strange acoustic effect that doesn't meaningfully occur on Earth, where sound of all frequencies travels at essentially the same speed through our much denser atmosphere. The specific numbers involved are worth stating directly, because they illustrate just how different Martian acoustics genuinely are from what we're used to. Researchers analysing Perseverance's recordings determined that low-pitched sounds on Mars travel at approximately 240 meters per second, meaningfully slower than the roughly 343 meters per second sound travels through Earth's atmosphere, while higher-pitched sounds travel slightly faster still, at approximately 250 meters per second, a genuinely unusual split that doesn't occur in Earth's atmosphere, because our air is dense enough that this kind of frequency-dependent speed variation becomes negligible. This means that if two sounds, one low-pitched and one high-pitched, were produced simultaneously at some distance from a listener on Mars, the higher-pitched sound would actually arrive slightly before the lower-pitched one, and genuinely bizarre acoustic effect with no real everyday equivalent on Earth, since our atmosphere is dense enough to keep all audible frequencies travelling together at essentially the same speed. Scientists studying this data have noted that this effect means a listener on Mars would perceive sound in a way that's subtly, genuinely different from human intuition, built entirely around Earth's own atmospheric acoustics, potentially making certain complex sounds, a piece of music for instance, or a voice with many different frequency components, arrive at a listener's ear slightly smeared apart in time compared to how the same sound would be perceived here on Earth. Perseverance's microphones also captured the sound of the rover's own laser instrument, called SuperCam, which fires a laser at Martian rocks to vaporize a tiny portion of their surface and analyze the resulting plasma to determine the rock's chemical composition. This laser strike produces an audible popping sound captured directly by the rover's microphone, and scientists have used subtle variations in the acoustic signature of these pops to gather additional information about the physical hardness and density of different Martian rocks, an entirely unexpected secondary scientific use for a microphone that was originally included on the mission largely for its outreach and engineering diagnostic value, demonstrating that even a tool built mainly to let the public experience Mars more vividly ended up providing genuinely useful scientific data as well. It's also worth mentioning NASA's earlier InSight lander, which touched down on Mars in November 2018, several years before Perseverance. Carrying an extremely sensitive seismometer specifically designed to detect Marsquakes, seismic vibrations travelling through the Martian interior, similar in principle to how geologists study earthquakes on Earth. While InSight's primary seismometer was designed to detect ground vibrations rather than airborne sound specifically, the lander's air pressure sensor, included to help scientists correct for the effect of wind and atmospheric pressure changes on the seismometer's ground-based readings, incidentally captured some of the very first data ever recorded regarding how Martian wind and atmospheric pressure fluctuations behave over time, providing an important complementary data set to Perseverance's later, more directly audible microphone recordings, together building a considerably more complete picture of how the thin Martian atmosphere genuinely behaves, acoustically and otherwise, than either mission could have provided entirely on its own. In practical terms, this means that if you are somehow standing on the surface of Mars without any protective equipment, an impossible and immediately lethal scenario given Mars's cold temperatures, thin atmosphere, and lack of breathable oxygen, but useful as a thought experiment, you would still be able to hear things: footsteps, wind, the operation of nearby equipment. But everything would sound noticeably quieter, more muffled, and would carry over much shorter distances than the equivalent sound would on Earth, since there's simply far less air present to carry the vibration outward before it dissipates. Perseverance's own microphone recordings captured the thin, whistling sound of Martian wind, described by NASA scientists as noticeably fainter and higher pitched than wind sounds recorded on Earth, along with the mechanical clicks and whirs of the rover's own instruments operating, all of it genuinely audible, in the fullest, most literal sense, because Mars, unlike the vacuum of interplanetary space, actually possesses a real atmosphere capable of carrying real sound. It's worth pausing here to explain exactly why thunder, the sound produced by lightning, works the way it does, because the underlying physics applies just as directly to any hypothetical lightning storm on Venus, or on any other world with a sufficiently dense atmosphere, as it does to a thunderstorm here on Earth. Lightning itself is an enormous electrical discharge, briefly heating the surrounding air along its path to temperatures hotter than the surface of the sun, roughly 30,000 Kelvin, in a fraction of a second. This near instantaneous, extreme heating causes the air along the lightning's path to expand explosively outward, faster than the speed of sound, creating a genuine shockwave, which then decays into the ordinary sound wave we recognize as thunder as it spreads outward and gradually loses energy. This is precisely why thunder rumbles and rolls, rather than producing a single sharp crack the way you might expect from a single instantaneous event. Different portions of a typical lightning bolt, which can stretch for several kilometers through the sky, are at slightly different distances from any given listener, meaning the sound from the closest part of the bolt arrives first, followed by sound from progressively more distant portions arriving slightly later, blending together into the extended rumbling sound we associate with thunder rather than a single crisp bang. On Venus, where the atmosphere is so much denser than Earth's, this same basic physical process would likely produce a genuinely different acoustic experience. Any lightning discharge occurring within Venus's thick atmosphere would create a shockwave and resulting thunder that would probably sound deeper, more resonant, and would likely be audible over considerably greater distances than the equivalent event on Earth, precisely because sound propagates so much more efficiently through Venus's dense, atmospheric medium. Whether Venus actually experiences lightning at all remains a subject of ongoing scientific debate. Various spacecraft missions and Earth-based observations have reported potential signatures consistent with lightning activity within Venus's thick, sulfuric acid-laden cloud layers, though the evidence remains less definitive than the well-established, continuously observed lightning activity on Earth, and scientists continue to debate whether the electrical conditions within Venus's atmosphere genuinely support the same kind of large-scale electrical discharge process responsible for terrestrial thunderstorms. Saturn, meanwhile, provides one of the most dramatic confirmed examples of lightning activity anywhere else in the solar system, detected not through direct visual observation, since Saturn's thick cloud layers largely obscure any lightning flashes from outside view, but through radio emissions. NASA's Cassini spacecraft, which orbited Saturn from 2004 until its deliberate planned destruction in the planet's atmosphere in 2017, detected radio signals consistent with lightning discharges occurring deep within Saturn's massive storm systems, sometimes occurring in bursts and patterns that scientists nicknamed Saturn electrostatic discharges. Based on the intensity and duration of the electrical activity detected, planetary scientists have estimated that individual lightning bolts within Saturn's atmosphere may release many times more total energy than the largest lightning bolts ever recorded on Earth, a genuinely staggering amount of raw electrical and acoustic energy, generated deep within an atmosphere so thick and so massive that no spacecraft has ever been built capable of surviving the descent required to directly record what that lightning might actually sound like up close. This pattern, atmosphere present, however different in density or composition from Earth's own, means sound exists in some genuine, physically real form. Atmosphere absent means sound simply cannot exist in that location at all, holds consistently across every world in our solar system with a meaningful atmosphere. Titan, Saturn's largest moon, possesses an atmosphere even denser than Earth's own at the surface, composed primarily of nitrogen with a haze of complex hydrocarbons, and would very likely support the transmission of sound extremely well, though no microphone has ever successfully recorded audio there either. The European Space Agency's Huygens probe, which landed on Titan's surface in January 2005, carried scientific instruments, but no dedicated microphone specifically designed to capture ambient environmental sound. Though its descent instrument did record some acoustic data during its parachute descent through Titan's thick atmosphere, providing at least partial evidence of what atmospheric sound propagation on Titan might genuinely be like. The Huygens mission is worth dwelling on a little further, because it remains, to this day, the only spacecraft to have ever successfully landed on a world in the outer solar system, and its journey down through Titan's atmosphere offers a genuinely rare, real data set for understanding sound propagation somewhere so far from Earth. As Huygens descended by parachute over the course of roughly 2.5 hours, its instruments recorded data on wind speed, atmospheric density, and pressure at various altitudes throughout the descent, allowing scientists back on Earth to reconstruct a detailed profile of exactly how sound would behave at different heights within Titan's thick, hazy atmosphere. Because Titan's atmosphere is composed primarily of nitrogen, similar in that specific respect to Earth's own predominantly nitrogen atmosphere, but colder and under different pressure conditions overall, researchers have calculated that the speed of sound near Titan's surface would be slower than on Earth, though not nearly as dramatically reduced as on Mars, since Titan's atmosphere, unlike Mars's thin one, is actually somewhat denser than Earth's at the surface, despite the moon's small size and weak gravity. A genuinely counterintuitive combination that makes Titan one of the more interesting worlds in the entire solar system for thinking carefully about how acoustic physics might differ from place to place. Jupiter and Saturn themselves, despite being enormous gas giants without any solid surface at all, possess such deep, dense atmospheres that sound waves almost certainly do propagate through their thick, roiling layers of hydrogen and helium, likely producing sounds entirely unlike anything ever heard on any rocky world, generated by their own colossal storm systems, including Jupiter's Great Red Spot, a storm larger than Earth itself that has been continuously raging for at least the past several hundred years. Though no instrument has ever been built capable of surviving deep enough into either planet's crushing atmospheric pressure to directly capture and transmit that audio back to Earth. NASA's Juno spacecraft, which we've discussed on this channel before in relation to Jupiter's intense radiation environment, has provided indirect evidence of atmospheric activity deep within Jupiter through its radio and plasma wave instruments, detecting signals associated with Jupiter's powerful auroras and lightning storms, themselves genuine electromagnetic phenomena rather than literal sound, but consistent with an atmosphere turbulent and electrically active enough that real acoustic activity, thunder generated by Jovian lightning, storm-driven pressure waves rippling through the deep atmosphere, almost certainly exists somewhere within Jupiter's roiling, multi-thousand-kilometre deep atmospheric layers, permanently and completely inaccessible to any instrument humanity has yet managed to build. Before we turn to the psychological experience of true silence, it's worth addressing one more common point of confusion, because it involves possibly the loudest event most people will ever witness, in person or on video, a rocket launch. Rocket launches are, without question, among the loudest human-generated events on the planet. The Saturn V rocket that carried Apollo astronauts to the moon produced sound levels at launch estimated at around 200 decibels, measured close to the launch pad. A sound intense enough that, if experienced unprotected at close range, could cause physical injury through the sheer force of the pressure waves alone, since sound at that intensity stops behaving merely as something you hear and starts behaving as something closer to a physical mechanical shock wave capable of vibrating internal organs and rupturing eardrums. NASA and other space agencies employ substantial engineering measures specifically to manage this, including massive water deluge systems that flood the launch pad with hundreds of thousands of gallons of water in the seconds around ignition, specifically to absorb and dampen the acoustic energy before it can damage the rocket's own delicate payload or surrounding infrastructure. But here's the detail worth highlighting directly. Every bit of that tremendous sound is produced within and travels through Earth's own dense atmosphere, exactly the same physical medium responsible for carrying every other sound we experience in ordinary daily life. As a rocket climbs higher, leaving the thicker, lower layers of the atmosphere behind, and ascending into progressively thinner air, the intensity of the sound it generates, from an observer's perspective on the ground, actually is affected by this thinning atmosphere, contributing to why a rocket launch sounds so different, and progressively quieter and more distant, as the vehicle climbs higher into the sky. By the time a rocket reaches the edge of space, roughly 100 kilometers up, generally recognized using the internationally accepted Karem line as the boundary, it has already ascended well beyond the layer of atmosphere, thick enough to carry any meaningful sound back down to an observer on the ground, and continues from that point onward, to accelerate through progressively thinner atmosphere and eventually true vacuum, generating exactly the same total sound-incapable silence we've discussed throughout tonight's entire video, despite the fact that the rocket engines themselves continue burning with, in a very real physical sense, exactly the same tremendous combustive violence they exhibited moments earlier at ground level. Fully capable of producing sound, but with progressively less and less atmosphere available to actually carry that sound to anyone who might otherwise want to hear it. This creates a genuinely strange and rarely discussed reality. Astronauts inside a spacecraft during its ascent to orbit do continue to hear the engines firing beneath them, though considerably muffled compared to how the launch sounds from the ground, because that sound reaches them through the solid structure of the spacecraft itself. Structure-borne conduction once again, the vibration of the engines transmitted mechanically through the rocket's own frame directly into the crew capsule, rather than through the thinning, and eventually entirely absent, outside atmosphere. But any hypothetical observer floating in space just outside the ascending spacecraft, watching the same rocket engines burn with exactly the same tremendous output of energy, would, once the vehicle passed beyond the atmosphere thick enough to carry sound, witness the remainder of that same powerful ascent in complete silence. An extraordinarily strange split reality where the exact same physical event, a rocket engine burning at full power, is simultaneously one of the loudest sounds a human being can survive hearing, and entirely, totally silent, depending on nothing more than whether or not there happens to be enough atmosphere nearby to carry that sound to whoever's trying to listen. Let's return for a moment to a question we touched on earlier in this video, but which deserves a more complete answer before we close. What would it actually feel like, physically and psychologically, to exist in a genuinely soundless environment, the way an astronaut on a spacewalk effectively does, cut off from the ordinary vacuum-borne sound that space itself cannot carry, relying entirely on the small, self-contained bubble of air inside their own suit for everything they can hear? Researchers who study extreme sensory environments, drawing on work conducted in anechoic chambers, specially engineered rooms designed to absorb virtually all sound reflection and eliminate essentially all ambient noise, have found that complete silence, sustained for extended periods, produces a genuinely strange and often unsettling psychological effect on the human mind. The human auditory system, it turns out, did not evolve to process the total absence of sound. In the near-total silence of the world's quietest anechoic chambers so acoustically dead that they've been informally recognized as among the quietest places ever measured on Earth, visitors have reported becoming acutely, almost uncomfortably aware of the sounds their own bodies produce, their own heartbeat, the flow of blood through their ears, even the subtle sound of their own joints moving. Sounds that are always technically present, but are normally masked entirely by the low-level ambient noise of everyday environments. Most people, according to researchers who study these chambers, find it difficult to remain inside for more than a relatively short period, and several visitors have reported the experience becoming disorienting, occasionally provoking mild dizziness or a subtle but distinct sense of unease, precisely because the brain, deprived of its usual baseline of ambient auditory information, begins to fixate on whatever internal sounds remain. The technical engineering behind these chambers is worth understanding briefly, because it illustrates just how difficult genuine, near-total silence actually is to manufacture, even under deliberately controlled laboratory conditions. Anechoic chambers achieve their extreme quiet through a combination of two separate strategies: heavy external isolation, thick, specially engineered walls, floors and ceilings, designed to prevent essentially any outside noise, traffic, footsteps, electrical equipment, even the building's own structural vibrations, from penetrating into the chamber at all. Combined with internal wedge-shaped foam or fiberglass baffles, lining every interior surface, including the floor, specifically engineered to absorb sound waves generated inside the room itself, preventing them from reflecting back and creating any echo whatsoever. The combined effect is a room where sound is neither able to enter from outside nor able to bounce around and linger once produced inside, creating an environment that measures on a standard decibel scale at levels so far below the threshold of ordinary human hearing that specialized equipment is required just to confirm how quiet the room genuinely is. Some of the quietest chambers ever constructed have measured at negative decibel levels, meaning they are quieter than the theoretical threshold of average human hearing itself. A genuinely difficult engineering feat that requires eliminating not just external noise, but the chamber's own internal building systems. Air conditioning, electrical hum, plumbing vibration, anything at all capable of generating even the faintest measurable sound. Even these extraordinary engineered chambers, representing some of the most acoustically isolated environments human technology has ever managed to produce, still don't achieve the complete total silence that exists as an ordinary, unremarkable baseline condition throughout the overwhelming majority of the physical universe. An anechoic chamber, however quiet, still contains ordinary air, meaning any sound genuinely produced within it, however faint, technically remains capable of propagating according to entirely normal acoustic physics. The chamber is simply engineered to prevent that sound from being audible or from reflecting and building up. The vacuum of space, by contrast, doesn't merely suppress or absorb sound. It removes the physical possibility of sound propagation entirely. A more fundamental, more absolute form of silence than any laboratory chamber, however sophisticated, has ever been able to reproduce. Precisely because space isn't engineered to prevent sound. It simply lacks any of the physical matter sound would need in order to exist there in the first place. This is worth connecting directly back to the experience of an astronaut on a spacewalk, floating outside a spacecraft in the genuine total silence of the vacuum beyond their suit. A silence considerably more complete and more permanent than anything even the quietest anechoic chamber on Earth can produce, since an anechoic chamber, however acoustically dead, still contains ordinary air capable of carrying whatever sound genuinely exists within it, while the vacuum outside a spacesuit contains no air at all, no medium of any kind capable of carrying sound, meaning the astronaut's own suit and its internal systems, their own breathing, their own heartbeat, and the voices of mission control relayed through their headset become, quite literally, the only sounds that exist anywhere in their immediate vicinity, the entire remainder of the universe surrounding them rendered totally, permanently silent, regardless of how much might be happening within it. Astronauts who have conducted spacewalks have described this experience in strikingly similar terms across many decades of missions. A profound, almost meditative quality to working in complete visual and auditory isolation from the vast environment surrounding them, punctuated only by the sound of their own breath and the occasional voice of a crewmate or ground controller, a sensory experience genuinely unlike anything replicable anywhere on the surface of Earth, however quiet the room. There's one more genuinely important clarification worth making before we move toward the closing themes of tonight's video: how astronaut radio communication actually works, since it might seem, at first glance, to contradict everything we've established about sound requiring a physical medium. When an astronaut speaks to mission control, or to a colleague working nearby during a spacewalk, that communication doesn't actually involve sound travelling through the vacuum of space at all. Instead, a small microphone inside the astronaut's helmet captures the sound of their voice, which does exist as a genuine, ordinary sound wave, since it's produced and travels entirely within the pressurized air inside their helmet, and converts it into an electromagnetic radio signal. Precisely the same fundamental category of phenomenon as visible light or the radio waves emitted by a pulsar, which requires no medium whatsoever and travels freely through the vacuum of space at the speed of light. That radio signal is received by an antenna elsewhere, whether on the spacecraft, on another astronaut's suit, or back on Earth, and converted back into an electrical signal that drives a small speaker, recreating an audible sound wave once again, but only within whatever small pocket of air happens to exist near the receiving speaker itself. In other words, astronaut communication in space involves sound at only two specific points: inside the sending astronaut's helmet and inside the receiving listener's helmet or headset, connected across the vast, silent gulf of space between them, not by sound at all, but by genuine electromagnetic radiation, which neither needs nor uses any physical medium to make the journey. This is worth appreciating as a genuinely elegant technological solution to an otherwise insurmountable physical problem, since sound itself cannot cross the vacuum separating two astronauts, or an astronaut and mission control on Earth. Engineers simply convert sound into a different, medium-independent form of wave for the actual journey. Then convert it back into sound only once it safely reaches an environment, a helmet, a spacecraft cabin, a room on Earth that contains enough air to make ordinary sound possible again. Every single radio transmission ever sent from space, from the earliest crackling voice transmissions of the Mercury and Gemini programs in the early 1960s to the routine, everyday communications aboard the International Space Station today relies on this exact principle, silently working around the vacuum's fundamental prohibition on sound by translating that sound into something the vacuum has no problem carrying at all. This same principle explains, more broadly, why every single sonification project we've discussed tonight, the Perseus black hole, Voyager's plasma waves, pulsar timing data, the cosmic microwave background, ultimately depends on exactly the same underlying trick, taking some form of data, whether a genuine pressure wave trapped within a dense medium, or electromagnetic radiation that never needed a medium in the first place, and converting it into an electrical signal capable of driving an ordinary speaker, recreating audible sound only at the very final stage of an otherwise entirely soundless journey across the vacuum of space. It's the same basic engineering principle radio communication has relied on since the earliest days of spaceflight, applied here not to carry a human voice, but to carry scientific data across distances and through media that no literal sound wave could ever have crossed on its own. There's a considerably more dramatic and violent example of the same underlying principle worth mentioning as well: supernovae, the explosive deaths of massive stars, among the most energetic events in the entire universe. A single supernova can, for a brief period, outshine an entire galaxy of billions of ordinary stars combined, releasing an amount of energy in a matter of seconds that dwarfs anything else that regularly occurs anywhere in the observable universe. And yet, exactly like every other event we've discussed tonight, a supernova produces this staggering energy release in the near-total vacuum of interstellar space, meaning that despite being, in every meaningful physical sense, one of the loudest events the universe is capable of producing, in terms of the sheer raw energy of the shockwave involved, it would be entirely, completely silent to any hypothetical observer floating safely nearby, exactly the same way the sun's own violent convection and flares are entirely silent beyond its outer atmosphere. The shockwave from a supernova does eventually interact with surrounding interstellar gas and dust, in some cases producing genuine, if extraordinarily slow and low frequency, pressure waves rippling outward through that surrounding material, not unlike the pressure waves detected in the Perseus cluster. But the initial explosion itself, however unimaginably violent, unfolds without producing a single decibel of sound capable of crossing the vacuum separating it from any observer, a genuinely humbling reminder that the loudest events the universe can produce and the complete absence of any audible sound are not, as intuition might suggest, mutually exclusive categories at all. It's worth taking a moment to appreciate just how deep, evolutionarily speaking, our relationship with sound actually runs, because it helps explain why the total silence of space feels so instinctively, viscerally strange, rather than simply unfamiliar in the way, say, an unfamiliar smell might be. The earliest structures, resembling ears, capable of detecting vibration and converting it into a signal a nervous system could interpret, are believed to have evolved several 100 million years ago, likely originating as simple vibration-sensing organs used by early aquatic creatures to detect movement and pressure changes in the water around them, well before anything resembling a modern ear, or even a modern animal, existed at all. Over the following hundreds of millions of years, as life gradually moved from water onto land, these vibration-sensing structures evolved and diversified dramatically, eventually producing the sophisticated, airborne sound-detecting ears found in modern mammals, including the specific eardromosical cochlear chain we discussed earlier, a chain of adaptations refined continuously across an almost unimaginably long stretch of evolutionary time, specifically to detect and interpret vibrations moving through some physical medium, air or water, surrounding the organism. This means that every single organism capable of hearing anything at all, from the earliest vibration-sensing fish hundreds of millions of years ago to every human being alive today, has only ever existed within environments containing some physical medium capable of carrying sound. There has never been a single moment across the entire multi-billion-year history of life on Earth when any hearing organism has existed anywhere except within an atmosphere or a body of water, both of which are, by definition, capable of transmitting sound. The total silence of space represents something genuinely, categorically unprecedented in the entire history of life as it has ever existed anywhere we know of. An environment none of the hundreds of millions of years of evolutionary refinement behind human hearing could ever have prepared us for, since no ancestor of any currently living species, at any point in the entire history of life on this planet, ever had to survive, hunt, communicate, or simply exist within a genuinely soundless environment until human beings first built spacecraft capable of carrying us there. There's a useful, if imperfect, comparison worth drawing here to the deep ocean, another environment often described, loosely and somewhat inaccurately, as a kind of alien frontier here on Earth. The deepest parts of Earth's oceans, the Mariana Trench and similar deep sea trenches, plunge to depths exceeding 10 kilometres, environments of crushing pressure, permanent total darkness, and temperatures barely above freezing, genuinely extreme by any measure of what most life on Earth is adapted to survive. And yet, even in the deepest, darkest, most crushing trenches on the entire planet, sound travels remarkably well, arguably better than it does through air, since water is a considerably denser medium capable of carrying pressure waves efficiently across enormous distances. Some deep sea whale calls have been documented travelling for hundreds, and in certain cases potentially thousands, of kilometres through the ocean's deep sound channel, a layer of water at a specific depth where temperature and pressure conditions combine to trap and efficiently propagate low-frequency sound waves across vast horizontal distances. This means that even the most extreme, most genuinely alien environment accessible on the surface of our own planet. A place of crushing pressure and total darkness that in many ways more closely resembles conditions on other worlds than anywhere else on Earth, still fails to replicate the one condition that makes space genuinely, categorically different from literally everywhere else life has ever existed. The complete, total absence of any medium whatsoever capable of carrying a sound wave, even a single centimetre. One worth naming directly before we close, because it connects tonight's story back to the broader themes this channel keeps returning to about distance, isolation, and what gets stripped away the further from Earth you travel. Sound, more than perhaps any other sense, is deeply tied to a feeling of connection, of shared presence with the world immediately around you. The ambient hum of traffic outside a window, the murmur of conversation in another room, the wind moving through trees, all of it constitutes a kind of constant, largely unnoticed confirmation that you exist within a living, active environment, filled with other things happening around you, whether or not you're paying direct attention to any of it. Space strips this away entirely, and does so more completely, more totally, than any environment human beings have ever had to contend with throughout the entire history of our species. It's not merely quiet, the way a remote desert or a deep forest at night might be quiet. It is genuinely, physically incapable of producing any ambient sound at all, beyond whatever small, self-contained bubble of atmosphere a spacecraft or a space suit happens to carry along with it. An astronaut floating outside their spacecraft exists, for the true first time in human history at that moment, within an environment that cannot, under any circumstances, produce the low, constant background hum of ambient sound every human being has experienced, without exception. For the entire recorded history of our species, going back long before recorded history existed at all, further back than our species itself, to whatever the very first sound-sensing organism on Earth ever experienced hundreds of millions of years ago. This is, in its own quiet way, one of the most genuinely alien aspects of space travel, stranger in some respects than radiation exposure or communication delay, because it touches something so fundamental to how living creatures on Earth have always experienced their surroundings, that it barely registers as strange until you actually stop and think carefully about it. Every environment life on Earth has ever evolved within, the deepest ocean trenches, the highest mountain peaks, the driest deserts, has still, always, without exception, contained some medium capable of carrying sound, some background hum of wind, water, or simply the movement of air itself. Space is the first environment human beings have ever entered that lacks this entirely. And it's worth remembering that fact the next time you watch footage of an astronaut working calmly outside their spacecraft, hundreds of kilometers above the Earth. Everything you're hearing in that footage, the astronaut's own breathing, their voice relayed to mission control, is being generated entirely within a small, fragile bubble of air a few centimeters thick, the only place. In the astronaut's entire field of view, extending outward for millions of kilometers in every direction, where sound is still physically possible at all. It's worth pulling one more thread together before we close, because it connects nearly everything discussed tonight into a single, unifying idea. Every exception to the space is silent rule we've explored, the sun's trapped internal convection, the Perseus black hole's million-year pressure waves, Mars's thin, frequency-splitting atmosphere, Titan's dense nitrogen haze, the lunar seismometers detecting moonquakes ringing for an hour through dry, brittle rock, shares exactly the same underlying requirement, some form of matter, gas, liquid, plasma or solid, dense enough and connected enough to carry a vibration from one point to another. Sound, it turns out, isn't really a property of loud events themselves. Explosions, storms, dying stars, colliding galaxies. It's a property of the space between things. A question not of how much energy an event releases, but of whether anything exists in the surrounding environment capable of carrying that energy onward as a wave. The loudest event in the history of the universe and complete total silence are not opposites at all. They can be, and constantly are, the exact same event, viewed from two different distances, through two entirely different surrounding media, one dense enough to carry the sound, and one that, however close, however violent the source, simply has nothing left to carry it with. This reframing is worth sitting with, because it changes how you might think about every future headline describing some new dramatic cosmic event, a merging pair of black holes, a newly discovered supernova, a storm system on some distant exoplanet. The underlying physical event may well be staggeringly loud, in the fullest, most literal physical sense of that word, releasing genuine pressure waves capable of carrying real acoustic energy outward in every direction. Whether any of that energy could ever reach an ear, human or otherwise, capable of actually hearing it, depends entirely on a separate second question, one easy to overlook amid the drama of the event itself. What, if anything, fills the space in between? Looking ahead, several upcoming and currently active missions are likely to add meaningfully to our still limited catalogue of genuine, directly recorded, extraterrestrial sound. NASA's Dragonfly mission, a nuclear-powered rotorcraft scheduled to launch in the late 2020s and arrive at Titan in the mid-2030s, which we've discussed on this channel before in relation to its unusual flight-based exploration strategy, is expected to carry instrumentation considerably more capable than Huygens' brief one-time descent measurements, potentially providing the first sustained, high-quality audio recordings ever captured from Titan's surface across a mission lasting years rather than a single 2.5-hour parachute drop. Future Mars missions, building directly on the genuine scientific and public engagement success of Perseverance's own microphones, are widely expected to continue carrying similar audio equipment as a matter of course, gradually building an increasingly rich, increasingly detailed record of exactly how sound behaves across different seasons, different locations, and different atmospheric conditions on the Martian surface, refining the already surprising frequency splitting discovery discussed earlier into an increasingly complete acoustic model of the entire planet. There remains, however, no realistic path, using any currently foreseeable technology, toward ever directly recording genuine audio from Venus's surface for more than the briefest possible window, given the extraordinary engineering challenge of building any instrument capable of surviving Venus's crushing pressure and scorching heat for long enough to be scientifically useful, nor any realistic near-term path toward capturing genuine atmospheric audio from deep within Jupiter or Saturn, environments where the atmospheric pressure increases so rapidly with depth that no spacecraft design currently under serious consideration could survive long enough to transmit meaningful data back before being crushed. These worlds, for the foreseeable future, will very likely remain among the last great, unexplored acoustic frontiers of our own solar system, places we already have strong theoretical reasons to expect are filled with genuine, dramatic sound, thunder, storm-driven pressure waves, roiling atmospheric turbulence, and yet remain, for now and likely for decades to come, permanently beyond the reach of any microphone we currently know how to build and successfully deliver there. That's where we'll leave things tonight. Not with an explosion, and not with a roar, but with a genuine, complete silence that fills the overwhelming majority of the universe. A silence so total that even the most violent events imaginable, a star's own death, a black hole's own faint, million-year pressure waves, unfold without a single sound ever reaching anyone unlucky, or lucky, enough to witness them from nearby. It's a strange thing to sit with, that the loudest possible universe and the quietest possible one are, in the end, the exact same universe, and the only thing separating them is whether or not, in that one specific place, something happens to exist for the sound to travel through. Somewhere above you tonight, an astronaut aboard the International Space Station is listening to the quiet hum of air circulation fans, the only sound available to them, in a location surrounded, in every direction, by a universe that has never once, in its entire 8 billion year history, made a sound loud enough for any of us to actually hear. Rest well.